Waves 7. Diffraction. What do we mean by diffraction? Diffraction is the bending of waves as they pass through a slit or a gap. It's also referred to as the bending of waves as they pass the end of the obstacle. Obviously an obstacle is just half a slit or a gap, and you'll see what we mean by that shortly. We explain it by using Huygens principle, which we learned earlier. Here's a photograph of a ripple tank. Here we're generating parallel wavefronts. This is a barrier and this is a barrier, so there's a little gap here, and these are the resultant wavefronts coming through the gap. And notice it's gone from straight wavefronts here to round or circular wavefronts here. And this is how we explain it using Huygens principle. Here's our incoming wavefronts. Here's the barrier. Here's the edge. Here's this wavefront, which is just the next wavefront. And if we consider each part of the wavefront to be its own source and generating its own wavefront, we've picked a couple of sources here, but they're all the parts, or all the particles in the medium are all generating their own wavefronts. These guys here are all constructively and destructively interfering, so that you end up with a new wavefront here at this point, progressing as it moves. This is like a time-lapse photo. However, notice that this point is generating a circular wave, but there's nothing to destructively interfere with it, and so you get this circular wavefront generating and going out in that direction. And that's the diffraction. This is just straight generation of a wavefront. It's not diffraction. This is the diffraction, this bending of the wave. And so diffraction is greatest when the wavelength is large and the gap is narrow. So here we have a short wavelength quite close together and a narrow gap, and this is our diffraction. Here we have a long wavelength and a narrow gap, and we've got more diffraction. And here we have a long wavelength and a long gap, and we can see that there's not as much diffraction. And so this is the case where you get the most amount of diffraction. And so basically the two corners are acting as point sources, and then you're getting interference, constructive and destructive interference. Diffraction is more noticeable when the size of the slit is comparable to the wavelength of the waves. So here the diffraction is highly noticeable because it's curved. Here, and we see this often, is these waves have just been passed through the gap without any interference. But there's our little bit of diffraction happening on the side. Not nearly as dramatic as the diffraction here. And so this is the case where you get the most amount of diffraction. Again, same thing. Again, this is the diffraction here. These are just being transmitted. Now there's a web page that I need to go to. Let's have a look. And it's over here. It's going to take forever for this to open up. Here we go. So we've got some animations here. I'll swap over to the mouse. Oh, my Windows is bugger off. Okay, here's our diffraction. So notice how the gap size equals the wavelength, the diffraction increases, and so the waves spread out. So if we slide this slide, okay, we're making the gap wider and you're only getting the curvature. We can pause it, and so that's the diffraction. If we make the gap smaller, we get more diffraction. Okay, so that's diffraction for a single slit. This is trying to simulate a ripple tank. So if we have a large slit, there's our waves coming through in the ripple tank, and we're getting a straight line and then curvature. Notice that they're trying to show that these waves are weaker, so they have less energy, so they have less amplitude, but they have the same wavelength. If we go for a medium slit, we should get some more roundness and more diffraction into areas that are shadows. But notice that most of the energy is in this wedge here, and there's only a small amount of energy dissipated. And if we go to a small, because only a small amount of energy, it's being spread out over a wide area, the amplitude will change. but the wavelength doesn't. So we're only taking a small amount of wave energy, but now spreading it over a larger area. If we go back to the large slit, we can see that. So most of the energy is here in this center wedge, and there's a small amount of energy going out around the corner. So down here I also noticed that this gives a nice little explanation of Huygens principle, which I'll run through very quickly. Here we have one source generating a round wave. Huygens imagined there are lots of sources generating lots of waves, and therefore you get the wave front happening. And this is what's happening with the going through a slit, is basically all these points are generating their waves, and you're getting a combination of all those waves producing what you actually see as the resultant diffraction. And so there's an area of where the wave is just transmitted, and then the area of diffraction. Alright, let's go back. Let's close that down because that was slowing everything up. And let's go back to our PowerPoint. So, oops, I need to go back, and I've also got another animation I'm going to quickly show you, and this one should work a little bit better. Here we go. Look at that, that's working fantastically. Here we go. And this will be on your OneNote. Here we've got water, we can use sound, and we can use light, and they all, because they're all waves, they all experience the same thing. Here's our diffraction. We can change the frequency and the amplitude. We can change, here we've only got one slit, and we can change the width of the slit, make it narrower, and notice the effect getting weaker, less amplitude, because only a small amount of energy is going through this gap, but it's got to be spread out over this area. Or if we make the slit wide, getting a lot more energy, but less diffraction happening. And we can do that in sound and light. So have a go at that on your OneNote. Let's get rid of that now, and we'll go back. So let's have a look at some natural examples. Here we have a barrier and there's waves coming in, and you can just make out curved waves. This is diffraction around it, and so a lot of harbours are actually built to block waves, but they suffer from diffraction. And this is a model in a ripple tank of a proposed harbour, and how they're trying to stop all the waves from getting in, because diffraction can be a problem, because some natural harbours actually become unsafe when the wave fronts are coming from certain directions. Here's a nice photo of diffraction again, curved waves coming in and being, so this here is acting as a point source. There's a natural harbour, and you can see that although the waves are a bit chaotic here, there is a wave pattern coming through, and you're getting a nice lot of diffraction right around that area. Now the apostles used to be called the 12 apostles, but now there's no longer 12 on the Great Ocean Road in Victoria. What have they got to do with diffraction? Well, this is how they form diffraction. You get the waves coming in from the ocean, and because of diffraction, the waves actually whip around, and waves are very erosive, and you get a little bit of erosion on the front, but this erosion here starts to undercut and eats in, and these two bits erode off a peninsula. For some reason this bit is a bit more resistant to weathering. Waves are weathering this bit as well, and eventually, because of diffraction, they'll cut this off. And sometimes you get a thing called a bridge, where it's actually completely undercut, but you still have some rocks on the top bit, and you can go across. Now we're also going to see some characteristics in waves. This is diffraction in a wave in clouds. The wind is blowing, and you've got a mountain range, and so you're getting these sorts of patterns here. Sometimes they're called standing waves as well. I think the next, this is just a weird pattern because of wind and air. Just thought I'd show you that one. It's real. Now these are what's called mountain waves, which are actually standing waves generated when wind goes over a mountain range. And you see these in Tasmania quite often, especially down south, where you get strong winds and they come off the ocean. And so if you look at the weather satellite pictures of Tasmania, you can sometimes see mountain, these parallel standing waves of mountain clouds. So in the next video we're going to look at two-source interference. That will do us for now. Bye.